Hi, I am Silvia Cruciani and I will guide you through our work in-hand manipulation of objects with unknown shapes. This work addresses the problem of finding a sequence of motions to change the configuration of an object inside the robot's gripper without having to release the grasp. I will refer to these motions as in-hand or in-gripper manipulation. In addition, we assume that the system does not have previous knowledge of what the object looks like, meaning that it will have to plan for in-hand manipulation using only the partial information on the object's shape that is available from the used sensors. Our system is composed of three main parts that I will describe later in more details. 1. Reconstruct the object shape. 2. Build a partial dexterous manipulation graph. 3. Use this dexterous manipulation graph to plan in-hand manipulation. This plan will then be tested with robot experiments. Now you might be wondering, what is a dexterous manipulation graph? Well, the method I will present is based on our previous work where we introduced the concept of dexterous manipulation graph, or DMG in short. This DMG is a representation of how a gripper's finger can move on the given object's surface, and it is obtained by analyzing the object's geometry in an offline step. We use this graph to plan motions of the object inside the robot's gripper. This dexterous manipulation graph, DMG, is a disconnected, undirected graph. Each node represents a position on the object's surface and a possible range of orientations that a finger can achieve when its tip is in contact with the object at this position. Two nodes are connected by an edge if it is possible to move between them using in-hand manipulation motions. We consider two possible motions: translation, in which the contact point between the finger and the object slides, but the finger's orientation does not change, and rotation, in which the contact point between the fingertip and the object remains constant while the finger's orientation changes. By using a combination of these two motions, the object can move inside the robot's hand and achieve a large range of reconfigurations. In our experiments, we exploit dual arm manipulation to execute the desired motion of the object inside the hand. One gripper pushes the object, while the other gripper is holding a grasp on it. We control the motion by tightening or loosening the grasp while the object moves, and by adapting the relative motion between the two robot arms. However, the same in-hand motions can be achieved also with a single arm pushing against an external contact. In this work, we have addressed some of the limitations of our previous work and designed a new method, which we called online DMG. Compared with our previous work, we now address the situation in which the object's shape is unknown and must be inferred from sensory data. The graph is not built in an offline fashion, but it is built at the same time in which we look for an in-hand manipulation solution. We have also changed the graph structure, making it into a directed graph to underline the fact that it is not always possible to revert a certain motion. In addition, the feasibility of a motion is directly checked when building the graph to improve the quality of connections between nodes. Finally, since we consider unknown object shapes, we associate each component of the graph to a quantity that defines the confidence or certainty that that part of the reconstructed object's shape is correct, so that planning in-hand manipulation can try to avoid motions that involve uncertain parts of the object. The first step in our system is shape reconstruction. We use a denoising version of variational autoencoders trained using data from the YCB object set to learn the shape prior of a set of object classes such as hammers, spoons, spatulas, etc. Once the object shape is obtained, we analyze its surface to build a graph, while at the same time searching for a feasible solution to move towards the desired graph configuration. We add edges to the graph only if it is possible to obtain the corresponding sliding motion by pushing against the object. For certain object shapes, it is only possible to push and move in one direction and not possible to push and move back, hence our decision to make the new graph a directed graph. We build the graph incrementally while searching for an in-hand manipulation solution. The nodes are expanded one by one along unexplored directions. New nodes are added to the graph, and the graph's components adapt and merge during this process. We use the term graph component to indicate the subset of nodes that belong to a connected component. Since the DMG is a disconnected graph, it is not always possible to find a path between two nodes. so it is not possible to move from one grasp configuration to another if they correspond to nodes that belong to two different components. This video shows an example of building the DMG while looking for an in-hand manipulation solution. The initial grasp points and fingers orientation are shown in red and the desired ones in magenta. The nodes are expanded until a solution is found. The green path shows the motion of the fingertip, and the yellow lines correspond to the finger's orientation along this path. The grasp components are expanded and merged as new tasks appear or as the search goes on. In this video, each node's color represents its component. One of the main differences with our previous work is the online process with which we build the DMG. Previously, the object's shape was analyzed offline and only then the graph would be used to plan in-hand manipulation. This figure shows a comparison between planning times using both the offline and online approaches. The time is shown in logarithmic scale. Here, we consider two objects and three different in-hand manipulation tasks to go from one grasp configuration to another. For these experiments, we provided both methods with the full object's shape to remove the uncertainty due to shape reconstruction that is only present in the new online DMG method. The orange and blue bars represent the time required for building and planning using the offline DMG. The green bars represent the online approach, always starting from the beginning. The red bars show instead building the graph incrementally between tasks, meaning that the first part of the graph is built for task 1, then we plan for task 2 by expanding this pre-existing graph, and then we also expand the resulting graph to plan for task 3. Finally, the purple bars show a similar experiment in which the third task is the same as the first. We can see here that the online DMG allows for building the graph faster, and consecutive tasks benefit from its incremental building structure. We compared the solutions obtained with our new method with and without shape reconstruction using YCB objects for the experiments where the full object's shape was required. These tables show the average position and orientation errors that were the outcome of in-hand manipulation solutions for different tasks on the given objects. We use the metrics defined in the in-hand manipulation benchmark that is shown at the bottom of the slide. In the second table, we also report the percentage of cases in which our method failed in finding a solution, although a solution exists. Each solution is a sequence of translations and rotations that move the object towards the desired grasp configuration. These motions can be achieved by pushing the object at a given point in a given direction. We use the second robot's gripper to execute the pushes. And here is an example of changing the grasp configuration of a hammer inside the gripper. This video shows the robot executing the in-hand manipulation solution. It pushes the object at the appropriate point to slide it and rotate it inside the gripper, and finally obtained the desired grasp configuration. And this concludes my presentation. Thank you for watching!